Hello, advanced algebra students. Welcome to another video lesson as we start to explore a new chapter to come to a conclusion here for the rest of the school year. We are going to start looking at exponential growth and decay situations, graphing some of the exponential growth, exponential decay, and really kind of using that to lead up into some new material to kind of finish up the year. So make sure that you've got notes ready, things lined up so that we can continue to progress. We are in a new chapter, so there will be a new packet with a lot of stuff linked out there as well. Again, exponential and logarithmic functions. So test one is really going to be more of review stuff, exponential growth, exponential decay, continuous compounding or regression, things that I know we've done in algebra. So we have to review it a little bit and talk about it a little bit more. But then test two is log stuff, which is almost all new. Different logarithms and properties of these logarithms and solving with logs, as they're called. So we'll get into that the second part of the chapter. But really the first part here is exponential. All right. And here's what I want you to consider as we explore exponential. It's called the Flamin' Hot Cheetos scenario. And believe it or not, I don't even think I've had one Flaming Hot Cheeto. I just don't like them. Yuck. So anyway, let's just say that you buy a Powerball ticket and you won the lottery, $1 million. Being the intelligent investor that you are, you decided to put all $1 million into the Flaming Hot Cheetos stock. After 1 year, your investment has grown to $1,050,000, and then after 2 years, your investment is now worth $1,102,500. If that stock continues to grow at that same exact rate year after year, how much money will you have in that stock after 50 years? Why don't you pause the video here and take a guess, maybe? What do you think? How much money would you have after 50 years? Okay, now, again, we could certainly create a table, something that we did in the past. After year one, we had, 1,050,000 after a year. So that's after year one. After year two, we had 1,102,500. We could figure out what percentage that's growing by to go to year three and figure out what percentage to year four and so on. But what this represents is what's called exponential growth. Okay, and we have a general equation for growth and for decay. Y equals A times B to the power of X. A times B to the power of X, where this A value out front is our initial value. What did we start with? Okay, cannot be zero. We didn't start with zero. We got to start with something. It's also our Y-intercept. It's where our graph starts. The B value right here is what we call a growth factor. A growth factor. Now, growth could be increasing or decreasing, so be careful with that. Exponential growth, if this B value is greater than 1, we have a problem that's growing and probably growing rapidly. And if that B value is between 0 and 1, we have exponential decay, where it's decreasing in value or amount. All right, so make sure, I would write this down right here in your notes somewhere, the general equation and what each of those pieces represent. Now, in order to help us with some of this, we can use the Cheetos example, right? Our initial investment was $1 million. There's our A value. And if you looked back and figured out what percentage it grew each year, right? Take the difference from year to year and divide by the original amount, you'd see that it rose by 5%, meaning this is 1.05. We're going to use a lot of percentages in these problems. If it's growth, 1 plus the percentage. If it's decay, 1 minus the percentage. But we've got to use the decimal form in here. And that'll be a key piece to remember. That you want to use that decimal form of the percent. Okay, and really we're just plugging information in, and then X represents the time, the years. Okay, and that way we can measure a value of something. Now, what we also want to be able to look at is the graph of these. Okay, we want to be able to look at the graph, and I'm just going to use y equals 2 times, let's go 4 to the power of x for one of them. So that would be a growth because my b value is greater than 1. And then I'm going to use y equals 2 times 1/2 to the power of x, where my b value is less. And we're going to look at domain and range for these exponential functions. So if I go back to Desmos and we're looking at the graphing, 2 times 4 to the power of x, and then let's close that. You can see there's my graph. Okay, domain and range is related to this. So here's my y-intercept at 0, 2. Domain goes with the x values. Okay, so this line, if I keep scrolling to the left, that line is red. It's going to keep going to the left, and it would also keep going to the right. It's not going to go as very fast to the right, but it will continue to grow. Let's look at y equals 2 times 1/2 to the power of x in the blue, right? So it's shrinking all of a sudden, but notice it would go back to the left. This blue line would just keep going back, and it would go on to the right forever. So the domain in both of these is all real numbers, all real. Okay, y equals a times b to the power of x. But let's look at the range, right? It's going up. Both graphs here in this case are going up as high as we possibly can for right now. But notice they're coming down, and what are they never crossing, right? The blue line looks like it's touching this axis down here. Right? It looks like it's touching the x-axis, but if I actually scrolled in and I kept scrolling in, it's actually never, ever, ever going to touch the x-axis. It just gets really, really close. So my range for both of these is always going to be y is greater than or equal to 0. Right? It's going to touch this. So we would intercept here at 4. It's growing, and eventually it's going to look like it's hitting it, but it's just, oh, that's the wrong way. That's a decrease one. Increasing left to right. I should have drawn it from the left to right going up. And it's going to increase, never touching the 0. Where if it's decreasing, we're going down left to right with a half of a parabola almost. All right, so make sure you just understand the difference there between domain and range. So let's just look at these two. Considering this function, f of x equals 3 times 2 to the power of x. Is that growth or decay? That is definitely growth, right? 2 is b, and is greater than 1. What is the y-intercept? It would be 3. All right, so we'd start the graph at 3. It's a growth, meaning from left to right, it is growing, right? 3 times 2 to the power of x. Y equals 3 times 2 to the power of x, and you can see it is, oops, I gotta zoom back out, and it is growing. 2 times 0.45x, growth or decay? That is decay. It is shrinking. 0.45 is less than 1. What's the y-intercept? The y-intercept is at 2, right? My a value. So it's here, but it's decreasing by 0.45. So, it's going to decrease and then all of a sudden just get really close to 0 if I keep drawing that way. All right, so you got to be able to identify some of those key characteristics in terms of y-intercepts and in terms of the growth or decay factor and how it actually is acting. Now, can you turn them into equations? Write an exponential function f of x that has an initial value of 25 and a growth rate of 17%. So f of x equals, right, it just wants us to write a function. So instead of using y, we'll use f of x. All right? And again, y equals a times b to the power of x. A is our starting value, so we're starting with 25. The growth rate is 17%, so in here I'm going to do 1 plus 0.17. Okay, when it's growing, we add it to 1 and we change it to the power of x, meaning f of x equals 25 times 1.17 to the power of x. It's growing by 17%. And now I could use that equation to figure out, how much will be this, what value will this have in 10 years or 20 years and so on. An exponential function g of x has an initial value of 25 and it decays at a rate of 25%. So if it's decaying, we have to take that away from 1. So 0.25 taken away from the 1. So we can say g of x, this growth function, is 25 times 0.75 to the power of x. Its decay rate, right? Its growth factor was a decay of 25%. So if it's growth, it's going to be 1 plus that percentage to the power of x. And if it's decay, it is 1 minus that percentage to the power of x. All right, and this is, again, I hope this is review and you recognize some of this from algebra. We're going to start to use this in story problems tomorrow, so make sure you have your calculators and decimals ready, where we look at populations, investing money, things that are called half-lives or doubling, cell division, a lot of different things that go along with exponential growth and decay. If you have any questions, please make sure that you reach out. Otherwise, until next time, everyone, stay safe.